Hey everyone, this is Mayur. Welcome to ML Works. In this video, we'll be talking about image denoising. This video is a follow-up on the previous video, which was autoencoder, where we built a simple autoencoder of generating an input image as an output. Okay, what is image denoising, right? Image denoising is nothing but a neural network which is capable of removing the noise from an image. The way the model gets trained is you have an image with the noise, and that will be your training data set, and you will also have a target. In this case will be the clear image of that particular noisy images. Now when the during the training process, the network tries to learn how to clean the image based on the input and the output. That is the target that is given. In this case, if you see in the image currently what we have in front of us, original plus noise, we have some noisy image at the top and a reconstructed image in the bottom. So the neural network tries to remove the noise from the image. So in this case, what we'll do is, in this particular video, we'll try to build a neural network convolutional autoencoder, which will try to remove this noise from the image and generate a much more clear picture than the original input image. Now let's import the packages. What is required? First is matplotlib for viewing the images, numpy and pandas for data manipulation, and then tensorflow for building the neural network. And then we have metrics, sklearn for evaluating the metrics, and then we have keras for building the neural network layers, and then loss functions, and then we have a data set to import the fashion MNS data set, and then we have model class. Now let's run this particular cell and import the package. After the packages are imported, we are loading the data. If you don't have the data set locally, you have this particular statement will download the data set and it will be stored locally. And then we are normalizing the data set by dividing it by 25 to 55, and such that the value of the pixel ranges between 0 and 1. And in this particular step, we are giving tf dot new access. We are currently, if you look at, if you don't give new access, the image dimension will be 60,000 cross 28 cross 28. And when we give tf dot new access, we are creating a new access with the dimension 1. And here, if you look at, we have text train of 60,000 images with dimension 28 cross 28 cross 1, and test data set with 10,000 images with the dimension of 28 cross 28 cross 1. Now this is a clear image. Here we don't have any noise by default. So to understand this image denoising, what we do is we take in a clear data set and we add some noise to this data set by a factor of 0.2 is the noise factor, and we also take in a 28 cross 28 normal distributed random numbers. Now once we then we multiply the noise factor with the normal distribution and then add it to the data set for both the train and test. And then we clip the, after addition, it could, what the value of this pixel could be go beyond 1 point something, or it could be something between less than 0 also as well. So what we do is we do it something called as clip by value, such that the value of the pixels remains between 0 and 1. Now I'll just run this particular cell. So let me run this one first and then run this first. Okay, so here what we do is we have created our noisy data set, and we will be what just plotting that noisy data set here, excess noise. And if you look at the images, the noise we can see on the images here clearly on the fashion, whatever shirts and pants, whatever we have some noise on top of it. Now what we do is we create a class for denoising the for the neural network architecture. Okay, where we pass in the input format, because since we have turned our input in such a way that it takes in a channel of one. Okay, we'll be passing that as our input dimension here under kras.sequential. These are the layers that is used for building the neural network architecture. In this case, this is the neural network for the encoder part, and this is the neural network architecture for decoder. And these two combined together, we form denoising architecture. So it takes in 28 cross 28 cross 1, and then we apply convolutional neural network and kernel size of 3 cross 3 and 16 kernels totally, and activation function of ReLU, and padding is same stride 2, Then we pass another convolutional neural network and the 8 kernels, 3 cross 3 is the kernel size. And then we have a decoder, which will be like exact opposite of what convolutional encoder is doing. We are convolutional decoder will do something exactly opposite. Here 2D transpose we are doing in decoder. So what will happen is, consider you have an image of 28 cross 28. It will be, since autoencoder normally what it does is it creates a bottleneck layer, and the decoder will try to generate image from the bottleneck layer. So in this case, what it will do is it will create a new convolutional neural network of the encoder, and it will generate some dimension of latent representation, and the decoder, which is this one, will try to generate the image, clean image out of that particular latent representation. So here we take in the output of this particular encoder and pass it to decoder, which is convolutional transpose here. And if you see exactly that dimension here, 8, 8, okay, and it is 16, again it is 16, and then it is again generating 1, which will be the 1 for this one. Okay, we are just going back again to the original image and its corresponding dimension. Now here, if you look at, this is the init function and this is the call function. First the encoder will take in and the input, and then the output of the encoder will pass to the decoder, and the decoded image will be passed as an output. Now here we have just declared this particular class and defined it. And next step is, let me run the cell. And here we are compiling the particular neural network, which is autoencoder. We are compiling it with the optimizer, Adam optimizer, and the mean square error. So just to understand, right, what is the mean square error will do here? In this case, the image will be, the input image will be a noisy image, and the target image will be the clean image. So it tries to reduce the noise or loss between these two. Okay, that's the whole point of this mean squared error. It tries to reduce that. So if you look at autoencoder.fit, it takes in extrained noisy image, and our target is the clean image, which is extrained. Okay, and we are running it for a epochs of 10 and shuffle the data set, and we have validation data, which is x-test noise and x-test. Now I'm not running this particular model because it takes quite some time. Okay, I'm just leaving it up, and just let's go to this particular place, which is autoencoder.encoder.summary. Let's understand the architecture, how the dimension will change, right, when you are running it. So if you look at the encoder, okay, it takes in, so this is, it takes in 28 cross 28 cross 1, and it generates something called as 14 cross 14 cross 16. 16 is the number of kernels that have been present there. Okay, 16 kernels of feature maps, you can call it feature maps, that would be a better word to say it. And the dimension of each feature map is 14 cross 14, and total parameters is 160. And then this will be passed to the next convolutional layer, and there you will have the dimension of 7 cross 7 and 8 feature maps. The total number of parameters are 1160. Now this will be passed to the decoder, and the decoder will try to regenerate the image, which is a clear one. In this case, if 7 cross 7 cross 8 will be passed, and it will generate 14 cross 14 cross 8, and that will be turned into 28 cross 28 into 16, and they will get the original image back at the end. So that's the decoder summary. So I'm saying this is okay. Let me just remove. It's not required to look at. Okay. So what we'll do here is autoencoder.encoder will take in the just since we have trained the model. Okay, as I trained the model here. Okay, just to be clear, right? So first we x-test noise is passed to the encoder. We get it encoded images. The encoded images is passed to the decoder, and everything is in the NumPy format. That's what. Yeah. Now, once that is done, we can plot that particular encoded and decoded images. So let me go to this particular cell right here. We have x-test noisy, which is this particular images at the top row. And then we have decoded images, which is after the model has taken the noisy images and has generated a clear image of that. So this is the reconstructed images. So we can clearly see that the noise have been removed from these particular noisy images using this particular neural network architecture. So this is one of the application of autoencoders where you can remove the noise from the image. In the real time, if you have images which has noisy pixelated images, then you can train a model with the corresponding image which are clear, and try to remove the image noise from the images which has noise. So with that, I'll be concluding this video. Thank you so much.